All right, so how is lab 1 going? Anyone running into trouble? Okay, we're gonna do an exercise. So I'm gonna have everybody close your eyes and raise your hand if you have no idea what's going on with lab 1. Okay, so and then you can open your eyes. So if you raise your hand, you're not the only one. There are quite a few people who have been having trouble with it, and that is totally understandable. This kind of language of tensors and dimensions, and it's probably one of the hardest things to get down. So I definitely encourage you to come into the TAs and try to get some help on that. TAs are awesome. Actually, we haven't gotten a chance to introduce them yet. So we have Matthew up here in the front. Is Nate still here? I think Nate was in here before he just left. And then Ben Havens, is he here? All right, so the reason why they are not here is because they are trying to hold more office hours so they can help you more. So yeah, they're experts at what they do, and they will be able to definitely help you with these labs. Okay, so today we are going to come back to where we ended last time, which was matrix vector multiplication. Yeah, question.
Does the future lab take modules?
Yes, first lab is by far the easiest. Sorry. Yeah, labs in general, past this first lab, you can probably expect to spend like between 4 to 9 hours. So yeah, they're pretty extensive. So yeah, matrix vector multiplication, if you remember. Sorry, do we have another question? Yeah. So the question was, if you have your own GPU, can you train on that? Absolutely. So you're not required to use Colab. That's just a convenient way to get access to GPUs if you don't have one. Okay. Yeah. No, not necessarily. All right. Any other questions? Okay. Oh, yes.
Can we just do the entire lab?
I'm not sure I understand your question. Do you have?
Because you can share your file on lab. Where do you want?
Yeah. So the way to submit the files is to download your finished IPython notebook from Colab and submit it to Learn this week. We're not doing sharing or anything like that. Make sense? Okay. Yeah.
You want the format to be
correct. Yeah. IPython notebook. Mm-hmm. All right. All right. Matrix vector multiplication. Any more questions? Okay. Cool. So yeah, as a brief review, matrix vector multiplication is basically a sequence of dot products where the result of every dot product gives us a single number in our output vector. For dimensions, the second dimension of this matrix has to match the first dimension of this vector in order for matrix vector multiplication to be compatible. Now, what does this mean in like a real world training a neural network application? We're going to skip that exercise. And actually, we're not going to the application quite yet. So this is just matrix multiplication, and it's exactly the same thing, except rather than having one vector and getting one output vector, we now have multiple vectors, and so we get multiple output vectors. And so you can see that when you do matrix multiplication, the inner dimension, which matches between the two matrices, disappears, and you're left with a tensor that has dimensions A by C. which are the first dimension of the first matrix and the second dimension of the second matrix. And you can think of it as every entry in that A by C matrix contains a dot product between the ith row of the first matrix and the jth column of the second matrix. All right, so yeah, now we're going to look at a practical example of how of translating this into the language of images, image classification. So this is a core task in computer vision. Given an image, tell me what is in that image. And so we'll assume that this image contains one of these following 10 labels. The problem is that when we see this image, we see colors, but when we translate an image into numbers, the computer sees something like this. And so our job is to train the computer to look at that and translate that into the concept of a cat. So in this case, we have an image with 300 rows and 100 columns. And then, does anyone know where this 3 might come from? Yeah.
Red, green, and blue.
Red, green, and blue. Yeah. So this is, if you were wondering in the lab for this Saturday, what are we doing with more than 2 dimensions in these tensors? What could that third dimension represent? Well, here's an example. So we have height, width, and then cans. And each entry in this 3-dimensional tensor contains a number between 0 and 255, representing the intensity of that pixel value. But there's some challenges with this. What if we were to change the camera? What if we were to tell our neural network that this is a cat, but then we change the camera angle, so now we're looking at the cat from above? We now have a different set of input pixels, and the network somehow needs to be able to know that it's still a cat. Another challenge is illumination. So you might, I don't know if you can tell, but we have 2 cats, a dark cat and a light cat, and they obviously are very visually different and have completely contrasting pixel values. So somehow needs to be able to deal with that. Oh yeah, good idea. Is that better? Okay.
Jacob?
Yes. Good question. I did not make these slides, so I don't know. But you could probably generate a photo that looks a lot like it using Dolly or Stable Diffusion, like we saw last time. Another problem is deformation. So we have cats in all kinds of different fun poses. So we have to be able to handle different poses as well as different lighting and visual angles. Occlusion. We have a cat sticking its head out of couch cushions, or standing behind a water tank, or hiding behind a curtain. Background clutter. You have a shag cat on a shag rug. How can you identify where the shag cat is? Interclass variation, different varieties of cats. So if you can imagine that if we were to code up an algorithm to, like hard code an algorithm to go through each pixel and identify whether there's a cat in this image, it would take a very long time to code up that program. Yeah, there's no obvious way to hard code the algorithm for recognizing a cat or other classes. But there is a function. Our brains perform it all the time, right? So this is a training problem called, or a data set called the CFAR10 data set. It's associated with the problem of, given an image, tell me which of these 10 categories that image came from. We have trucks, ships, horses, frogs, dogs, etc. 50,000 training images. Each image is 32 height, 32 width, and 3 channels. And then there's a test set of 10,000 images where you can evaluate your trained model. So this is going to be our approach. This is how we're going to use a neural network to approach this problem. We are going to call our image X, and we're going to have a weight matrix W that will map from the dimension of our input image into our 10 different class scores. And so to start off with, we will, because we're doing matrix vector multiplication, we will flatten this 3-dimensional tensor into a single vector, one long list of numbers that would have 3,072 numbers, which is 32 times 32 times. So if we want to go from 3072 into 10 class scores, can anyone tell me what the dimensions of our weight matrix W should be? Yeah? 3072, let's see. That would be 3072 rows by 10 columns. And then how long is our input vector X? Yeah, 3072. So are those dimensions compatible? 3072 by 10 multiplied by a 3072 by 1 vector. No, yeah, you were close. So yeah, we're going to switch it. So it's going to be, yeah, 10 by 30, set W will be 10 by 3072. So that we're able to multiply that by a vector of length 3072 and get out a vector of length 10, which will represent scores for each class. Okay, it looked like we had a couple of questions out there. No? Yeah, in the back. Why 10? Yeah. So we know that there are 10 classes in this data set, and so we want to predict scores for each of those classes. Does that make sense? Okay. So yeah, there's your answer. And then there's, in most neural network layers, we also have this bias vector. And we'll explain a little bit more what that does in the future, but basically it helps us learn a much more robust function than just learning the weight matrix. And the bias vector will have the same dimension as the output vector. All right, so let's have an example. So we're going to pretend that this cat image is actually only a list of 4 numbers because our slide is not very big. And we're going to have a weight matrix where each row of the weight matrix represents a class that we are trying to classify. And so if you remember, when we do matrix vector multiplication, when we do matrix vector multiplication, we're going to do a dot product between this vector and each row of that matrix. So think about that for a second. We're doing a dot product between the input image and each row of the matrix. So can someone try to explain to me intuitively what you think might be happening and why this might be useful? Yeah, in the back.
Yeah, we're sure this.
Exactly. And because if you remember, dot products represent similarity. And so we're going to basically compute the similarity between our input vector and each class.
Like class, do I red green? Like the channel based on colors.
Oh, no, good question. So the colors represent different classes. Yeah, so in this case, this is blocking it, but red is cat score. What was that? That would be really nice, wouldn't it? Oh, I like that. Okay. Thank you. So yeah, red is kind of our cat score. Green is our dog score, and blue is our ship score. And you just did a beautiful job of explaining what this linear classifier does. It basically tests the compatibility of our input image with any of the classes. So I want you to take a look at this slide for about 30 seconds and see if you can figure out what each of these images represents. And so each of these images represents one row in that weight matrix. And yeah, try discussing with the person next to you as well. What do you think these kind of blurry images represent? And like, why do you think they look the way that they do?
I guess things like computational training so the areas where you see the horse one.
I think it's just like this, and that way when it's last.
So are these like the like dividends around the weight matrix? That's right. So it's I think it's a little goofy because it's
Okay.
yeah.
So yeah, what ideas do you have of what these images might be and why they work the way that they do? Yeah. Exactly. Yes.
The reason they look like that is that's
Right. So I'm gonna repeat that for the video. So what he said is exactly right. So each of these represents one row in the weight matrix, reshaped back into 32 by 32 by 3, and it's what he said is it's what the computer sees when it sees a bird or a cat, etc. Exactly. Any other thoughts maybe on how these kind of blurry images might relate to the data that the network was trained on? Yeah.
Sorry.
She can
Sounds like you have a question first.
Yeah, just to clarify that each one of those represents a row.
Yeah. So each of these images, we remember how we stretched out our 32 by 32 by 3 image into a long vector. Now we're taking this, doing the same operation except in reverse to take that vector and turn it back into an image.
Yeah.
And specifically, we're doing it for the vectors in the weight matrix. Yeah. So
because these are color images, and we can see that we start at 0 as dark, meaning a low weight or no weight, and white being maximum on all 3 channels as being a high weight. You can see the brighter parts of these images are sort of the consensuses of the training data. So if you look at the horse, you can sort of imply that you can almost see a horse facing left and a horse facing right, but they sort of agree in the middle with the torso. So you can see, oh, there's a bright area there, less so in the legs because slight variation is very sensitive per training data image.
exactly. I love what you said about kind of a consensus of the training data. That's exactly right. And so you can kind of think of these, and it turns out that when you train a linear classifier, you end up with each of these images in your weight matrix basically being the average of all of the images in your training set. Hey, yeah, Olivia. That's a great question. Yeah. So the question was whether for a given model, it only classify certain sizes of image. And the answer is that it depends on the model. There are some models that are, you're right, they can only deal with fixed size inputs. The other models that are trained to operate on inputs of varying dimensions. Okay, yeah, question.
If this ends up being an average of all the data set, why are we training? Why don't we just take the average?
Great question. So the question was, why are we training a neural network if we could just take the average of all the images in the training data? And the answer is that for our simple linear classifier, we could. And if you think about it, that could be thought of as a way of training this classifier is by taking the average and just finding, we would call it like the nearest neighbor no, this would not be nearest neighbor. But basically, yes, seeing which average image our test image is closest to. But when you get into larger, deeper neural networks, it actually turns out that the last layer of every deep network is a linear classifier. But all of the layers going up to that point basically transform your input image gradually into a prototype image of the desired class, so that it will, so that the linear classifier at the last layer will work. Okay, other questions? Okay, so interpreting this linear classifier. We're now going to try to understand what this diagram is showing. So imagine that instead of a 32 by 32 by 3 image, we have a two-dimensional image called X, where we have X1 right here and X2 on the y-axis. And we will have our CAT score be a neural network, WX plus V, that assigns a score of how likely a given two-dimensional image is to be a cat. Two questions. Number one, what is the domain and the range of this score function? Yeah, in the back. R2 is the domain or the range? Yeah, so you're right. So the domain is R2. Yeah, so the range here, because we're just generating a single number, a scalar, the range will be just R, the real numbers. So this function S, it maps from R2 to R. Good with that? Then the second question is, what are the dimensions of W and V in this scenario? Yeah, Michael?
W is 3 by 2.
W is 2 by 3. How did you get that?
There's 3 classes. You have 2 dimensions. So 2. That depends on what X is.
Great. So yeah, so I should clarify. So sorry, this diagram doesn't perfectly correspond to what we're talking about here. It will in a second, but for now, we just have a score function for cats. And so actually we're just predicting one single number, and we only have, because there's only one class, and our input has dimension 2. So you had the 2-part correct. The output dimension, Travis, do you have a thought?
I just had a clarifying question. This CAT score, are we ignoring like our classifier here? Is that what's the CAT?
Yeah,
Or-
so you could say, let's just say it's car instead. So
Okay, so
car score, and we're just trying to, ignoring the rest of this picture, we're trying to find something that will tell us how close we are to being a car.
this CAT score is like one of
Kind of. So I think it'll make more sense in a couple of slides. So I'll just give you the answer. So the dimensions of W are 1 by 2 because it's taking an input vector of dimension 2 and producing a single number. The dimension of B is 1 because WX has dimension 1, and so in order to do addition, it needs to have dimension So, we're going to have our cat score. Score of x is wx plus b. And we can plot the score function on a 3D graph where we have x1 and x2 as our cat, as the numbers in our cat vector, and z represents the cat score. And this is what you get when you, this purple plane is what you get when you plot S of x equals wx plus b. Now, a score function doesn't tell us yes or no whether something's a cat. It just tells us this is more like a cat, this is less like a cat, right? So in order to turn that score function into a classifier, we need to pick a threshold that tells us everything above a certain score is a cat. And so we can plot a function t of x, threshold of x equals some constant, and plot that right here. And that's just going to be a plane in that intersects only the z-axis, and which will intersect with our classifier. And then, yeah, every x, so every set of x1 and x2 values for which the score function is higher than the threshold, we will say that that is a cat. And then if we look at this line where the threshold and the score function intersect, and we plot that back on our two-dimensional graph, that then becomes a line that for which everything on one side of that line is defined, we consider to be classified as a cat. Does it make sense how we got to that point? Yeah, question.
So what would we do, for example, our car classifier and deer classifier if it's an image that ends up right in between, you know, like
right here?
no, farther to the right where
Right
it's
here?
beyond, yeah, in that space.
Great question. Yeah, so we've been talking about that is the perfect question. So we've been talking about score functions and single class classifiers. But yeah, how can we take all of these individual single class classifiers and turn them into multi-class classifiers that instead of telling us yes or no for a given class, tell us which of all of the 10 classes we're classifying. And that is exactly what we're going to look at next. So yeah, this is just reviewing. We have a score function for each class. These are the results of passing this image into each of those score functions, this image into each of those score functions, and this image into each of those score functions. You can see that our network does well for the first two because the highest, well actually, no, it does not. So this one, the true score, cat, is kind of in the middle. This one, the true score, is the best, so that's good. This one, the predicted score is not anywhere close to the highest. But this is exactly the question that you just asked. So how do we then create a multi-class classifier? And so we have access to a score function for each class that gives us this list of numbers. Does anyone have any ideas of how we could turn that into a multi-class classifier? Yeah, in the back. Yeah, that's a great idea. Great idea. And in fact, that is what we're going to do. So yeah, wx plus b gives us this vector of numbers, and we just pick the max, and that's how we turn these score functions into a multi-class classifier. Any questions? Okay, yeah. So using a linear classifier, probably not. But this idea of assigning scores and predicting scores and then choosing the max score is absolutely something that's done all the time. Yeah. often these scores are translated into probabilities, which is actually what we're about to talk about next. And so we can, by normalizing these scores in a certain way, which we'll talk about, we can turn them into probabilities, but it turns out that the highest scores end up having the highest probabilities, so it's functionally equivalent. Yeah, it's done all the time. Yeah. So, yeah, good question. Not exactly. Yeah, not quite. Although I guess you could kind of think of this score vector as saying like this image is most close to an airplane and kind of like a ship and kind of like a train, but not at all similar to a dog or a horse. So an embedding, for the if you are unfamiliar with the term, is a vector of numbers that represents your input, and that is not the original input. So it's some sort of kind of downstream representation of your input data. Yeah. Totally. Yeah, absolutely. Well, so yeah, you could have a 10-dimensional space, but you can also think about taking all of our images, predicting the score vector for each of them, and treating it as an embedding, like you were saying, and then you can project that embedding, that 10-dimensional embedding, down into a 3-dimensional space and visualize how close different images are to each other in that space. If you're interested, look up T-SNE, T-SNE, or UMAP, UMAP, or also just PCA. So those are the UMAP, T-SNE, and PCA are 3 pretty common dimension reduction approaches that you can use to take one of these vectors and kind of visually plot it in a 2D or 3D space. All right, we are on to the next lecture. So we have 2 quiz questions first. Question: if W has dimensions 6 by 10 and X has dimensions 10 by 1, how many dot products are involved in computing WX? You can just shout it out.
106.
6. Not 100. Okay. Okay, so this is probably the coolest lecture in the class, in my opinion. Well, maybe, I don't know. It's a very mathy lecture, but what I love is when I learned about loss function and gradients, my reaction was, why didn't they tell me about this when I was taking calculus? Like, why were we talking about all of these derivatives and things like that? To me, loss functions and gradients are one of the coolest examples, and neural networks in general are one of the coolest examples of where you can translate real world ideas into the language of math and do amazing things. So that is not applicable because we're a little ahead of schedule. So again, in the last lecture, we hit linear algebra, dot products, hats of many varieties. We talked about how to make a linear classifier, and we talked about score functions and then how to combine those score functions to create a multi-class classifier. And skip that. So in this lecture, we're going to talk about a loss function called the negative log likelihood or cross entropy loss, and how you optimize or find the minimum of that loss function. So this is just as a kind of an aside. This is a website where that has a bunch of different applications of AI in action or potential applications of AI. So a couple of these are playing Battleship, copying your handwriting, giving you fashion advice, inventing recipes, designing a chair, designing clothes. So you might, if you're interested, you can check this out. It's called Deep Index, and you might get some inspiration for your final project. Okay, so we know how to use a train classifier to assign scores and pick the max. How do we train it? The way that we train it is we first define a loss function. And you can think of a loss function as the opposite of a success function. So we have to define some sort of mathematical function that quantifies how happy we are with the scores. And then we'll call the unhappiness function our loss function. We want to minimize our loss, minimize our unhappiness. In other words, maximizing our happiness or our success. And then once we define that metric of success, we have to come up with a way of efficiently finding the parameters W and B that minimize that loss function. And I don't remember who it was had the idea we could just take the average of all of our images, and that would be an option for a linear classifier. But for these more complicated networks, we're going to use some fun other tricks. Okay, so we're going to simplify our 10-class example into a 3-class example. We have cats, cars, and frogs. With some W, we're going to just randomly initialize W. We're going to get scores for each class. So these are not the entries of W, these are our score vectors for each of these. And so you can see we're doing okay on cats, doing great on the car, and not doing very well on our frogs. So to define our loss function, we are going to treat these scores as unnormalized log probabilities. Basically, in other words, we want to somehow turn these scores into probabilities. And so this is going to be our objective. This is called the negative log likelihood loss. And so we're going to look at this equation and try to figure out what's happening. So can someone try to explain to me what they think is happening on this side of the equation, the left side? Yeah. Yes. Yeah, exactly. So this is called a probability model, and this is going to be the output of our neural network. And we're going to interpret the output of our neural network as a conditional probability because it takes as input our input image and predicts a class for that input image. And so to turn these scores into probabilities, this is how we do it. We're going to take e to the sk, which is the score for the k class, and divide it by the sum over all classes of e to the sj, where sj is the score for any of those other classes. Can someone try to explain in plain English how this function right here, how they think this function is helpful for turning these numbers into probabilities? Yeah.
Yeah, so the e to the s is
going to be the exponential function. So a larger number is going to represent a larger value in our exponential function. And we're going to normalize over all the values. So theoretically, values like, for example, in this one, the car with 5.1 will end up with a higher value in the exponential. And when we normalize over all the values, we're going to get supposedly like a probability-like number, even if it's not like a true probability. It's going to spit out for every class of probability.
Great, that's a great way of describing it. So yeah, to reiterate that, we're going to take the exponential of our score. And what that does is it turns all numbers, negative or positive, into positive numbers. The exponential function looks like this. It starts at 0 and it goes up as you approach infinity. So that has the benefit of making all of these positive, which we need in order for this normalization part, the dividing by the sum, to work. So if all of your numbers are positive and you divide by the sum of all of the entries in the vector, you will end up with the entries in the vector adding up to 1. Okay, I think we have a hand back there. Did you have a comment as well? Okay. So let's see what this looks like. And yeah, the right side of this equation is called the softmax function. And that's how the softmax function will turn scores into probabilities. Yeah, question.
So, really, what does the J represent in that equation?
Good question. So J indexes different classes.
Okay, so J is classes.
K also indexes classes. So yeah, good. It's good to make this distinction. So K is the index of the true class. So K in this case, cat is class 0. So K would be 0, and then J would be 0, 1, and 2 as we go through the sum.
Okay,
Make
and
sense?
then S would be the 3.5 negative.
Yes, exactly. So S would be the score vector, and then SK would be the 0th item in that vector, which is the score, which is the cat score. So what we're going to do is we're going to take the cat score and take the exponential of it and divide that by the sum of all of the exponential of all of the other scores. Okay, yeah, well. Great question. I think that would work. There are some nice properties, like optimization properties that the softmax function has that the absolute value function does not. For example, the absolute value function is not continuously differentiable, which might cause some issues. So yeah, we'll just say that for now. People usually use softmax. Okay, yeah, so we want to maximize the log likelihood, or for a loss function, minimize the negative log likelihood of the correct effects. Question? Actually, you're totally right. And I think that's the true answer. So thank you for that. Yeah, that is the correct answer. Is that I think the key is that the exponential is a monotonic function, meaning that it doesn't go down then up, and so it maintains the ordering, makes everything positive while maintaining the ordering of your scores. Thank you for that comment. Okay, and then yeah, so we're going to for the ith image, our loss will be the negative log likelihood of the true class given the input image. And that is our metric for success. That's where we will leave off for today.